Hello! Hello, everybody. Welcome back. I hope everyone's having a wonderful day so far. I am ready to stream today. Let me let the Discord know that we are live. All right. Whoops, wrong one. Bring back my OBS here. Okay, great. Let's connect to the stream here so we can get the chat loaded up. Like that. There we go. All right, hello, welcome back. My name is Michael. Hope everyone's having a wonderful day so far. We are back on today's Thursday, December 5th, 2024. We are back doing independent self-studying of Python, more specifically that of data structures and algorithms in Python. We are currently reading the PDF of data structures and algorithms in Python. This can be found either online, you can do a simple internet search, or if you would like, I provide a Discord, a community Discord, where I conglomerate all my study materials into one location. So if you're interested in having access to those resources, please see the description below for that link and feel free to join. It's completely free. So, yesterday in our studying, we continued with the 7 functions that we will go over in data structures and algorithms. We did a lot of review going over these 7 functions because we really need to know them quite well for understanding, these materials. And so, uh, yeah, and I think we have a pretty good definition so far of these functions. So we're moving on to 3.3 here for asymptotic analysis. All right, let's go ahead and continue. In algorithm analysis, we focus on the growth rate of the running time as a function of the input size n. In algorithm analysis, we focus on the growth rate of the running time as a function of the input size n, taking a, quote, big picture approach. For example, it is often enough just to know what the running time of an algorithm goes proportionally to n. We analyze algorithms using a mathematical notation for functions that disregards constant factors. Namely, we characterize the running times of algorithms by using functions that help map the size of the input n to values that correspond to the main factor that determines the growth rate in terms of n. This approach reflects that each basic step in pseudocode description or a high-level language implementation may correspond to a small number of primitive operations. Thus, we can perform an analysis of an algorithm by estimating the number of primitive operations executed up to a constant factor, rather than getting bogged down in language-specific or hardware-specific analysis of the exact number of operations that execute on the computer. As a tangible example, we will revisit the goal of finding the largest element of a Python list. Okay, we first used this example when introducing for loops on page 21 of section 1.4.2 code fragment 3.1, a function named find_max for this task. Okay, so we have a function here called findMax, which is our goal is to, given some sort of iterable data list, we want to find the maximum integer. So the biggest equals to the first initial point within our list, because that, if we're going to start with it. So for every value in our data, if the value is greater than the current biggest saved value, then we override it to that biggest value and return it. So this is a classic example of an algorithm with a running time that grows proportional to n. Right? As our data increases, it has more and more data to sort through, so it grows equally proportional to n. So this would be a linear, right? This would be, what kind of function would this be in a sense? If it grows proportional to n, is that just a linear function? No, that's equal to n. So we don't know if it's directly equal to n. So we'll see here. That grows proportional to n as the loop executes once for each data element with some fixed number of primitive operations executing for each pass, right? You're going to evaluate these conditions, right, for each pass. In the remainder of this section, we provide a framework to formalize this claim. LOL, hee hee, thanks so much for joining today. I appreciate you coming in and learning with me. I hope you're doing well. He says, they say I have another good resource for my DSA class. The professor is really good, passionate about this topic, and his notes are amazing. Well, awesome. If you're in the Discord, feel free to post it and do the chat on the Discord, and I'll check it out. Thank you so much for that. I would love to look at that resource. And thank you for joining us today. It's good to hear from you again. You're becoming a regular on here. All right, so we're learning about big O notation. So how did I kind of outline this before? Okay, big, quote, big dash O notation. Okay. All right, we're getting into it here, guys. This is the moment we've been waiting for. All right. Let function f of n and g of n be functions mapping positive integers to positive real numbers. Right? Let functions f of n and g of n be functions mapping positive integers to positive real numbers. We say that f of n is O of g of n if there is a real constant c greater than 0 and an integer constant of n of sub 0 is greater than or equal to 1, such that function f of n is less than or equal to constant times function g of n for n is greater than or equal to the initial n value. This definition is often referred to as the big O notation, for it's sometimes pronounced as f of n is big O of g of n. Figure 3.5 illustrates the general definition. Okay, so we have this guy here. So we have f of n is less than or equal to c times g of n. For n is greater than or equal to n at position 0. Thank you so much. I'll look forward to getting that resource from you, but I appreciate you stopping in for the time you do have. Thank you. Okay, so we're going to look at this figure here. So we have an initial input size here, right, of first input size. So as our input size grows, our running time for our initial function also grows, here in sort of a curve, but maybe almost linear, but kind of looks like it levels off. So then our function c times g of n at that same input takes more running time. Interesting. The function 8n plus 5 is O of n. Okay. So we have this function here, 8n plus 5 is an O of n. Okay, so let's see what this means. Justification. By the big O definition, we need to find a real constant, c is greater than 0, and an integer constant that is greater than or equal to, that the first value for our sample is greater than or equal to 1, such that 8 times 8n plus 5 is greater than or equal to cn for every integer of n that's greater than or equal to n at the first index. It is easy to see that a possible choice is c equals 9, right? So if we did c equals 9 and n equals 5, and the first index equals 5. Indeed, this is one infinitely many choices available because there's a trade-off between c and n index 0. For example, we rely on some constant c equals 13 and n equals 1. Okay, this is kind of annoying. This does not explain hardly anything that well. Zach the Shooter, thanks so much for coming. Do you have a schedule, and if so, how many hours do you do in the day? Yeah, I work 9 to 5. I work a regular 9 to 5 job, and then I stream anywhere from around 7 to 9 o'clock. Today I got off a little bit earlier, so I decided to hop on at 6 o'clock. I usually post announcements in the Discord about when I'm going live. Okay. The big O notation allows us to say that a function f of n is less than or equal to another function g of n up to a constant factor, and in the asymptotic sense, as n grows towards infinity, right, as our sample size grows larger and larger, as n goes towards infinity, okay, this ability comes from the fact that the definition uses less than or equal to compare f of n to function g of n times a constant c. For the asymptotic cases when the current n value is greater than or equal to the first n value input. However, it is considered poor taste to say f of n is less than or equal to O of g of n, since the big O already denotes the less than or equal to concept. Likewise, although common, it is not fully correct to say f of n is equal to big O g of n, with the usual understanding that the equals to relation, because there is no way to make sense of the symmetric statement. F of n is O g of n. Function is O g of n. Okay. So we're just trying to explain time complexity, I think. Like, g of n is the time complexity of the function in relation to big O, which is multiplied at some constant greater than or equal to the first index value of the sample size. So at least that's what I'm kind of interpreting this as. Alternatively, we can say that function of n, f of n, is order of g of n. For a more mathematical incline, it's also correct to say function f of n, forgot what that symbol means. For a big O notation, technically speaking, denotes a whole collection of functions. In this book, we will stick to representing big O statements as f of n is big O g of n. Even with this interpretation, there is considerable freedom in how we can use arithmetic operations with the big O notation. And with this freedom comes a certain amount of responsibility. Okay, characterizing running times using the big O notation. The big O notation is used widely to characterize running times and space bounds in terms of the parameter n, or our input, which varies from problem to problem, but it is always defined as a chosen measure of the size of the problem. For example, if we are interested in finding the largest element in a sequence, as with the find max algorithm we wrote earlier, we should let n denote the number of elements in that collection. Okay? Using the big O notation, we can write the following mathematically precise statement of the running time of the algorithm find max for any computer. The algorithm find max, which was above, which just found the maximum integer in a list of a data set of values, right? So the algorithm find max for computing the maximum element of a list of n numbers runs in O of n time. Justification. The initialization before the for loop begins requires only a constant number of primitive operations. Each iteration of the loop also requires only a constant number of primitive operations, and the loop executes n number of times. Therefore, we account for the number of primitive operations being c prime plus c double prime times n for appropriate constants c prime and c double prime that reflect, respectively, the work performed during initialization and the loop body. Okay, so if you have constant constants, right? You have to add the constants together to find the total time, respectively. Okay, because each primitive operation runs in constant time, we have that the running time of the algorithm find max of an input size n is at most constant times n. That is, we conclude that the running time of the algorithm find max is O of n. Okay, that makes sense, right? So we have this function here of find max, where we initially set the data point. This is going to be a primitive operation, setting a data point equal to one and to a new variable, right? We're going to do some sort of loop here, like a for loop, right? This is an operation, and then inside of this operation we do another operation. We check, and if that is true, we do this operation. So we have some constant operations that take place, right? So I'm not sure if you just count these one by one, but we have like a 1, we have 2, we have 3, and we have potentially a fourth check happening, a fourth check happening. Then you also have a return happening as well, which might be a operation in itself. So potentially you have 1, 2, 3, 4, 5 instances happening for potentially all the data sets in n. So your constant would be like 5 operations times the value of n, which in theory just represents the O of g of n, which is the number of constants that occur for any real constant, right? Because c is times g of n, which then takes place, which is considered O. So is big O just the sum of all constants of primitive operations in a algorithm? Because if that's what it takes place, right? If anybody has some input or wants to chime in, feel free. No, this can be collaborative and interactive. Totally. So just feel free to chime in if you want to discuss it all. Okay, so some properties of the big O notation. The big O notation allows us to ignore constant factors. Okay, so we ignore constant factors and lower order terms and focus on the main components of a function that affects its growth. So we have a polynomial here, right, where we have some value and then we are some coefficient, and then we append or add to our coefficient an n with increasing magnitude every time. So this polynomial is O of n cubed, because you have u to the degree of the polynomial, right? The highest exponent found within the polynomial expression is the degree of the polynomial. So justification, note that 5n not cubed. What's the word for exponents with the fourth power, or whatever? To the fourth power, 3n cubed, 2n squared, plus 4n plus 1 is less than or equal to 5 plus 3 plus 2 plus 4 plus 1 times n to the fourth is equal to cn to the fourth power. 4c equals 15 when n is greater than or equal to the first instance of n is equal to 1. Okay, so it's either less than or equal to the coefficients added together multiplied by the nth degree, which is equal to c of n times 4 to the fourth power. In fact, we can characterize the growth rate of any polynomial function. If f of n is a polynomial of degree d, that is, coefficient a is 0, coefficient in index 1, coefficient index 2, coefficient or index 0, index 1, multiplied by n, and so on to up to the nth degree. And the degree is greater than 0, then f of n is O of n to that degree. Okay, like we said earlier, we made that observation above, guys. All right, so justification for this, note that for n is greater than or equal to 1, we have 1, which is less than or equal to n, which is less than or equal to n squared, all the way up into the degree of the polynomial. So if we have for n is greater than or equal to 1, we start at 1, you go all the way up to the degree. Hence, the coefficients is greater than or equal to the absolute value of the coefficients plus all the way to the degree to the nth degree. Okay, we show that f of n is O of d of n of d, n of the degree of the polynomial, by defining c is equal to the coefficients added together, and n in the first spot is equal to 1. Okay, interesting. Get out of here. Get out of here. Get out of here. Get out of here. Sorry, guys. Bug was flying around. Okay. Thus, the highest degree term in a polynomial is the term that determines the asymptotic growth rate of the polynomial. We consider some additional properties for the big O notation in this exercise. Let us consider some further examples here, focusing on combinations of the 7 fundamental functions used in algorithm design. We rely on the mathematical design that log n is less than or equal to n for n is greater than or equal to 1. So we have a sample size of n greater than or equal to 1 for an input size, and then we have log n is less than or equal to n is our mathematical fact. Okay, so we have this polynomial here, right, which is just O of n to the nth to the largest degree of the polynomial, right? So you could take the coefficients, the absolute value of the coefficient, so 5 plus 3 plus 2 plus 5, 2 times the highest degree of the polynomial, so n squared is going to be equal to the constant times n squared. So our c, our constant, is just the coefficients of our polynomial added together. Interesting. So for this example here, right, we have constant of 20 plus 10 plus 5. So of 35 is our c value. So O of n to the third degree, right? This just has log is the highest degree in our polynomial is applied to the log n. So this is log n. Okay. So 3 log n plus 2 is less than 5 log n for n is greater than 2. Where did they get this less than 5 part? Oh, okay, less than or equal to 5 log n. They just added the coefficients together. They just reduced this down. So to 5 log n, when n is greater than or equal to 2. Note that log n is 0 for n is equal to 1. That's why we have to use 2 as our starting point for our minimum input value for log n. Okay. Interesting. So then in this case, when you have n in the exponents is O of 2 of n. So we have an exponential function here, and O2 of n. Justification 2 to the power of n plus 2 is equal to 2 of n to the power of n times 2 to the power of 2, which is 4 times 2 to the power of n. Hence, we take c is equal to 4, and our first place is 1 because this gets reduced down. Interesting. And then in this one, right, we have a log n and we have a regular n. So if we have a regular n to the first power, I believe that one overrides in this case accordingly. So O is big O of n. So justification 2 of n plus the 100 log n is less than or equal to 102 n. So interesting. In general, we should use the big O notation to characterize a function as closely as possible. While it is true that the function f of n is equal to this polynomial, is equal to, O big O of 5 prime, or n to the 5th power, or even, big O of n to the 4th power, it is more accurate to say that f of n is O big N of 3. Consider, by way of analogy, a scenario where a hungry traveler driving along a long country road happens upon a local farmer walking home from a market. If the traveler asks the farmer how much longer he must drive before he can find some food, it may be truthful for the farmer to say certainly no longer than 12 hours. But it is more accurate and helpful for him to say you can find a market just a few minutes drive up this road. Thus, even with the big O notation, you should strive as much as possible to tell the whole truth. Okay, so if we have a polynomial here, in general, we should use the big O notation to characterize a function as closely as possible. While it is true that the function f of n with a degree, polynomial degree of n to the 3rd power, is big O n 5, because we can sum these together, right, to get 7. Wait, no. No. You couldn't sum these, are not the same degree. So why is this O of 5? Or even big O n of power 4? Okay. It is also considered poor taste to include constant factors and lower order terms in the big O notation. For example, it is not fashionable to say that the function 2 of n squared is O of 4n squared plus 6n log n. Although this is completely correct, we should strive instead to describe the function as big O in simplest terms. Okay, so you have 2 of n squared, or 2n squared is big O of 4n squared plus 6n 4 log n. This is getting interesting. Okay. The 7 functions listed in section 3.2 are the most common functions used in conjunction with the big O notation to characterize the running times and space used of algorithms. Indeed, we typically use the names of these functions to refer to that of the running time. Indeed, we typically use the name of these functions to refer to the running times of the algorithms they characterize. So, for example, we would say that the algorithm that runs in the worst case time, that algorithm that runs in the worst case time 4n squared plus n log n is a quadratic time, right? Because this is to the nth degree here. Since the time runs in O of n squared time. Likewise, an algorithm running in time at most 5n plus 20 log n plus 4 would be called a linear time algorithm. Okay, because Okay, big omega. Hello, if you're watching, I appreciate you joining me today. I'm just reading Data Structures and Algorithms in Python. This is a textbook found online. It can also be found in the Discord below, linked in the description of the stream, where I just put a conglomerate of my study resources together. Hello, Anthony. Good to hear from you. I was wondering if you were going to pop into the chat today and give me a hand with some of this stuff. It's getting kind of challenging, if I'm being honest. I feel like I'm kind of getting it, but also it's pretty, there's a lot of jargon being used, and following all these polynomial functions is kind of difficult. I know they're just like examples, but it seems like polynomials. So if you have a polynomial with a logarithm inside of it, right? Like in this one, you have 2n plus 100 log n is in O of n time. It's not in logarithmic time. It's in linear time, because the highest degree of this polynomial is n to the 1st power, represented by this scenario here. Now, um, does now why is this n not considered in or like overridden in the time? You know what I'm trying to say? Why is or like why did they get how do they reduce this in this justification to where 102? So they obviously added the coefficients together. So in the worst case scenario, you will run at a time that is less than or equal to 102 n for every input size of n that's greater than or for initial input size is greater than initial, which is equal to 1. So our constants, so these coefficients or these c values, are these just the number of primitive operations that are within the function? Anthony says, yeah, so the idea is through simplification. We only consider the slowest growth factor within a polynomial. So in 2n plus 100 log n, the 2n would be the limiting factor in slowing down the algorithm. And 2 is a constant, so we can just reduce to n. Got you, because you don't display the coefficients in big O notation. So is by saying that this polynomial is less than or equal to the coefficients combined for the limiting factor in this case, which is linear time n, is this just saying that this is the worst case running time for this polynomial? Right? Interesting. So 2n. Now, my question was like, will be the limiting factor in slowing down the algorithm. So I thought, okay, so you have constant functions, logarithmic functions, then you have linear functions. Okay, so the linear function is the slower of the two functions provided in this polynomial, right? You have this section here that's going on within it, then you have this section going on, this part going on in the function. Now you have a bottleneck going on because this part is slower. So by default, this will be the worst case scenario taking precedent. Now, which is obviously just reduced down to O of n. Okay, this is interesting. Kevin De Lapez, thank you, thank you so much for joining me. I appreciate you coming in and leaving a comment. That's so kind of you. Thank you so much for spending some time here learning with me. He says, don't worry too much. The more you code, the more you will understand big O. Gotcha. Thank you so much for those kind words. Okay, so so then in this case, right, the log n is faster than the quadratic, so the quadratic would be our limiting factor or a limiting time constraint in this polynomial function. And so that's why we have a quadratic algorithm in O of n squared time, right? Whereas in this is in linear time, like the example above. Cool. Okay, big omega. Just as the big O notation provides an asymptotic way of saying that a function is less than or equal to another function, the following notation provides an asymptotic way, an asymptotic way of saying that a function grows at a rate that is greater than or equal to that of another. Okay. The following notation provides an asymptotic way of saying, okay, just as the big O notation provides an asymptotic way of saying that a function is less than or equal to another function, the following notations provide an asymptotic way of saying that a function grows at a rate that is greater than or equal to that of another function. So this is just saying in the inverse. So big O is refers to the limiting factor in our function, whereas omega talks about okay, so let's continue. Let f of n and g of n be functions mapping positive integers to positive real numbers. We say that f of n is omega g of n, pronounced f of n is big omega of g of n, if g of n is O of f of n. That is, there is a real constant, c is greater than 0. So we have constants, or operational primitive operations going on, and an integer constant with a starting in of greater than 1. Big omega so you have f of n is greater than or equal to the constant times g of n for n is greater than or equal to n at index 0. Anthony says, so big O describes the upper bound of an algorithm. Big omega refers to the lower bound. In other words, best case versus worst case. Okay, so this is considered worst case, right? And this is considered best. We'll come back and get a more formal definition on these for the notes purposes in a second. Okay, so this definition allows us to say asymptotically, asymptotic, this word sucks, that one function is greater than or equal to another up to a constant factor. So for this example, we have 3n times the log of n minus 2n. So let's first ignore what it says here, and let's try to figure out the big O notation of this example. So we have a linear function here. We have a linear function here, but this is encompassed by a logarithmic function here, being multiplied by a logarithmic function here. We have an n log n here with a coefficient 3 out front. So the n log n is going to be faster, obviously, than our linear function. So our linear this would be in big O of n time. Whereas when we're looking at the best case or big omega standpoint, this example would favor the faster function in our polynomial, right? Remember how we ordered these in our notes here, the 7 functions used in this book. We ordered these in order of, preference, is what the chat was kind of referring to it last time, right? These were ordered in terms of their desire. So we want constant, those are faster. We want logarithmic, we want linear. So no, actually, I take that back. I apologize. N log n is slower. So n log n, did I say that wrong, guys? So if big O is worst case, meaning that, why is n log n worse case than a linear function? Why is omega, you have an order from fastest to slowest. Okay, so constants, fast, logarithm. So then why would our best case scenario here be n log n? Big omega is n log n. When we have a linear function applied to this 2n right here. Oh, I'm thinking about this in the wrong way. Okay, so if you think about this, best case scenario means that this is as fast as we can possibly run, right? I was thinking about this inverted. Best case scenario is this is as fast as like if I'm a sprinter, right? If I'm a runner in a race, and I woke up feeling really good that day and was going to give the um, best race that day. Well, and I ran my fastest time. Boom, right? But if I woke up, feeling, sick or whatever, that would be my best case that day. I'd be limited by that. So my best case scenario would be n log n because it is slower than my linear function of n squared, right? Now, my worst case scenario would be that this would run in big O of n time, because at least because that's our fastest function. Interesting. So I kind of get the big omega part better than I get the big O part. Like the best case scenario um, being that it is dependent on our limiting. But I thought that that's like the whole point of big O, no? So so if we have a polynomial of this one right here, right? This is a cubic polynomial. This is a cubic degreed polynomial with a time condition of O(n) cubed, O of n cubed, because we have a degree 3 polynomial. Now, this is the worst case scenario because at the very worst, we are going to run as fast as this statement, n cubed, which is the slower of the functions, right? So n cubed is slower than n log n. So at the very worst, I'm kind of getting these confused, I feel like, between each other. So if big omega is the best case scenario, then it is limited. It you seek the limiting condition. Whereas big O notation is worst case scenario, so you seek the fastest condition or fastest function. Do I have that right? You seek the fastest function. Whereas in best case scenario, you seek the slowest function. Because you're in the best case scenario, you can only go as fast as your slowest function. But in the worst case scenario, you can only go as fast as your fastest function. That just doesn't, does that make sense contextually? Or like in the worst case scenario, explain worst case scenario in terms of big O so in terms of big O notation, the worst case scenario represents the maximum amount of time a space or given algorithm could take to complete, okay? Relative to the size of the input. It helps us to understand the upper bounds of an algorithm's performance when faced with the most challenging inputs. Characteristics of worst case in big O. Maximum effort. It assumes the algorithm process the most complex or time-consuming input. So you would seek out the slowest function here. But why, in this example, n log n is slower? No, it's faster, right, in my notes. N log n, no, n log n is slower than my linear function. So why am I bound? So if I put this in, this should give me big O of n notation, right? Growth rate n is very large. So identify the dominant terms. 3n log n grows faster than log n because then n squared, then sorry, 2n because log n grows, albeit slower than n, as n approaches infinity. As n approaches infinity, the minus 2n becomes negligible compared to the 3n log n. No, so this is big O of log n as well. So this is big omega of log n and big O of log n. Of n log n. Can that be the case? So 3n log n grows faster than 2n because the log n grows, albeit slower than n. Okay, let's do that, Anthony. Let's plot this. Come on. Okay. So we have f of n is equal to n log of n, right? And then we have f of n is equal to n. Okay. So when it talks about growing faster, it means it takes up more time faster for less inputs. It grows in the y column at a faster rate than that of here. Right, for only an input value of 79, you get 150, whereas on f of n, for an input value of 150, you get 150. Okay, so that's what it means by growing faster. So then big omega notation function is less than or equal to the function. If you plot n log n against n, you'll see that it grows faster, but it doesn't run faster because we aren't referring to actual time. We're referring to the asymptotic behavior. We're talking about the growth. It's the upper bound. So does big O is talking about the growth factor. It's not time. I thought that was the whole point of big O, was time complexity. So then y is big omega n log n for this same function polynomial. To explain why omega n log n applies to 3n log n minus 2n, let's analyze it in terms of big omega, which describes the best case lower bound or the minimum growth rate of function. Let's copy this into our definition here. I like that. describes the best case growth rate of a function, which describes the best case lower bound or the minimum growth rate of a function. Analyze for big omega. Focus on growth rate. The term 3n log n dominates as n becomes very large, even though negative 2n is subtracted. This is because n log n grows faster than n. Because n log n, okay, so we're focusing on the growth rate. So when we're focusing on growth rate rather than time, n log n dominates n, or a linear function, because this one grows at a faster rate than the linear function, right? Since omega looks for a lower bound, we only need to ensure that the function's growth is at least n log n for sufficiently large n. Describes the best case lower bound or the minimum growth rate. So in our notes here, n log n is a slower function overall, right, than a linear function. But it has a faster, because it has a faster growth rate. So growth rates are inversely proportional to function speed. That's my hypothesis from what I'm seeing here. So for big omega, which describes the best case or lower bound or the minimum growth rate of a function, meaning that it wants the slowest function. For when trying to figure out if a function is okay, so what can I say? Can I say does big omega then seek out the slowest function in the polynomial? Not quite. Okay, so big omega does not seek out the slowest function, but rather it identifies the lower bound or the minimum growth rate of a function for sufficiently large inputs. This means that big omega gives us an idea of the best case scenario or the slowest growth rate of the function that the function will have. But it focuses on the growth rate of the function as n increases, not necessarily the slowest part in the sense of being less significant. Clarifying big omega. Big omega describes the lower bound of a function. It tells us that no matter how large n gets, the function will never grow slower than a given rate. This is particularly useful for establishing minimum performance. In a polynomial expression like 3n log n minus 2n, 3n log n is the dominant term, meaning it dictates the function's growth rate as n increases. The term negative 2 minus 2n does not affect the value of the function for a large n. Its impact is still compared to which grows faster. In the case of 3n log n minus 2n, big omega focuses on the minimum growth rate of the entire expression for large n. Since n log n is the dominant term, it determines that the function will grow at least as fast as n log n, even though there are smaller terms like negative 2n involved. So then what determines that n log n is more dominant than n? The dominance of n log n over n comes from how these two terms grow as n increases. Growth rate comparison. Okay, so it all comes down to the growth rate rather than speed. I've been thinking of these things in terms of time, because that's what I thought that these were, but this is in terms of, or speed rather, this is in terms of growth rate. growth rate, right? So the worst case scenario, so growth, the dominance of n log over n comes from how these two terms grow as n increases, right? Growth rate comparison. N grows linearly with respect to n. If you double n, the function doubles, yes. N log n grows more quickly than n because the log n terms, even though it grows slowly, increases as n increases. This means that n log n grows faster than n, especially as n becomes large. Why is n log n more dominant then? Logarithmic growth. The logarithmic term log n grows slowly, but it still increases with n, even though log n is slow compared to linear terms. In terms of growth rate, right? Not speed. Even though log n is slow in growth rate in terms of linear terms, when multiplied by n, the overall expression n log n grows faster than just n alone. Asymptotic behavior. For large values of n, n log n becomes significantly larger than n alone. For example, if n is equal to 1,000, right, n log n 1,000 times 6.91, which is here n log n is much larger than n for the difference. Okay, so if you actually physically plug in numbers, then you can see the result. So big O and big omega notation. In big O or big omega analysis, we are concerned with how functions grow relative to each other as n becomes more arbitrarily large. I'm going to copy this. I like that definition a lot. Okay, so Anthony says, hey Vanch, thanks so much for joining. I appreciate you coming in. That's not what Anthony said, but yeah, Anthony says, in this function, both big O and big omega are going to be n log n because between n and n log n has the fastest growth rate and n log n has the slowest runtime. Okay, so is there a way to essentially, like a little statement that we can say, like a blanket statement that applies? Legendowski. I appreciate you coming in and leaving a comment on the stream. Thank you so much. That's very nice of you. Check out log 10 versus log 100 versus log 1000 versus log a million or whatever, and so on and so forth. Okay, so let's do that really quick. Let's do we need log base 2 of 10. Let's copy this. 100. Oh, we need a f then. I don't think we have a function. We don't have a variable though. Okay, so as you increase, you increase by the same amount every single time. It looks like a 3.32. You add the initial answer to every time. Okay, so what exactly does that tell us, Legendowski? Okay, as n increases, the impact of n log n term dominates because the logarithmic function slowly increases as n increases, making n log n grow faster than n. So big is a give me a blanket statement for how big O is determined. It describes the minimum performance or growth rate of an algorithm for sufficiently large inputs, focusing on the slowest possible rate at which the function can grow. In other words, big omega identifies the best case scenario or lower bound, ensuring the function will never grow slower at this rate. So determined by the function with the fastest I'm sorry, guys, if I'm spending a little bit too much time on these. I really just want to get these solidified in my mind so that when we build on top of them, I don't have any gaps. Ask Key, thanks so much for joining. Good luck with your learning journey. Best from Brazil. Well, I appreciate you leaving a comment, and I look forward to hearing from you again in the streams. Feel free to join along, and thank you so much. Ray313, what textbook is that? This is the Data Structures and Algorithms textbook. This can be found online, or if you would like to join the Discord link below, it's completely free. It's just a place where I have kind of compiled all my study resources into one location for the stream viewers. Um, so, so essentially, it is determined by the function with the fastest growth rate within our polynomial. Not quite, okay? It's not about finding the function with the fastest growth rate, rather the slowest lower bound that the function can grow at for large inputs. Clarifying the idea. Big omega seeks the minimum growth rate of the entire function, not the fastest one. Yeah? It guarantees that the function will grow at least as fast as this rate, regardless of the specific input. Okay, we understand that. So the dominant term, the one that grows the fastest, often determines this lower bound because it dictates the growth rate of the function as it increases. All right. Corey Animations, thanks so much for joining. I appreciate you coming in and leaving a message. Thank you. That's very kind. So the dominant term is often the fastest growing part of the function, but big omega concerns itself with the minimum growth rate, the slowest rate that the function can grow. Okay. I just don't understand why it would not be determined by the function with the fastest growth in the polynomial. Right? Like, is that not our bottleneck? Is that just the easy way to put it? It's probably going to give me the same thing, not quite again. Yes, you're right. When determining big omega, the dominant term in the polynomial is which is typically the term with the fastest growth rate, often sets the lower bound. Big omega is determined by the term in the polynomial with the fastest growth rate because that term dominates. Okay, so we are right in that instance. Okay. So it's determined by the function with the fastest growth rate, which is the fastest increasing y value for increasing x inputs. All right. Let's get caught up on the chat here. Legendowski says, I just wanted to point out the impact on time complexity of a logarithmic solution. So 1000 versus log 1000. Got you. In seconds. Okay, so like in terms of a linear function versus, so if you have log 1000 versus 1000, right, if you have log base 2 of 1000 provides you an output of 9.96, whereas having an input value of n equals 1000 would give you a value of 1000. So this function would be faster right? It's overall faster. No, it's not faster than the function. It if this provides an output of 9.96 or 9.97, what does that tell us in relation to just having n equal 1,000 for f of n equals 1,000? So I'm trying to wrap my head around. F and g aren't necessarily polynomials. Okay, that yeah, they can be functions. And okay, gotcha. Basically, if your code is n squared plus 2n, then n squared will always be your upper bound because it's way bigger than what 2n would ever be. This is true because if you had infinite inputs, then 2n would be negligible with respect to the n squared growth. Got you. Okay. All right, let's keep moving on here, guys. Throwing another thing at us here. Big theta. Notation. Okay, so in addition, there's a notation that allows us to say that two functions grow at the same rate up to constant factors. We say that f of n is big theta g of n, pronounced big f of n is big theta of g of n, if f of n is big O g of n, and f of n is omega g of n. That is, there are real constants c prime is greater than 0 and c double prime is greater than 0, and an integer constant of n index 0 is greater than or equal to 1, such that c prime times g of n is less than or equal to f of n, which is less than or equal to c double prime times g of n, for n is greater than or equal to n index 0. Wow, that's a lot of stuff. This is C single prime out here. This is C double prime. Sorry guys. G of n, there we go, there we go. All right, big theta is average growth, so middle bound. Since big O is the worst case scenario, you drop or ignore the terms that would not affect runtime significantly. Since big O is the worst case scenario, which means the slowest that the operation can run, right? You quote unquote drop or ignore the terms that would not affect runtime significantly. Big O is the worst case scenario, which means the slowest it will run. So is dependent upon the slowest function, right? You seek that is dependent upon the slowest function with the slowest growth rate. Hunter Script, thanks so much for the kind words. I really appreciate you hopping into the chat and leaving a message. You can read the n underscore 0 part by saying, quote, eventually f will be sandwiched between c prime g and c double prime g. Okay, so yeah, obviously, yeah, like what it says in here is you're less than or equal to, so you're in between for some constant values. You're at in between these constants, right? Chris, thanks so much for leaving a comment. Yeah, when thinking of big O, just imagine n is a really big number, i.e. 10,000. So if you do n equals 1,000 in n squared, it will be way slower than log n. Okay, gotcha. Because it's a larger number, right? Just off of the sheer calculation of it, right? So if you have log of 1,000 versus n, or 1,000 squared. So 1,000 squared provides you a value of 1,000,000, whereas log base 2 of 1,000 provides you a value of 9.96, which is a lot smaller. So what does the linear function is slower than the log function by quite a bit, by a lot of it actually, right? The log function with a base 2 performs this task with an output value of performs this function, with an output value of 9.96 or 9.97 compared to 1,000,000 for the exponential, or for the quadratic function. Now for just a linear, it would just be 1,000, right? Because n equals 1,000. So in this case, our log function is faster, it has a lower output. And then obviously the next one would be the log. So it's kind of interesting, guys, that you have such a drastic decrease, like between logarithmic function and a linear function for a large output value. Like if you put like 1,000,000 in here, let's say, right? Just like 1,000,000 compared to compared to 20. Like that's the magnitude of difference that these outputs provide between these two functions. So then what output does n log n provide at that point? So if we do 1,000,000 times log of 1,000,000, that's 100,000 there. That gives us 6,000,000. So that's 6 times greater than the linear function, and a whole magnitudes greater than the log function. Wow, interesting. Let's get caught up in the chat here, guys. Sorry I'm getting behind on the chat. I'm just kind of thinking this through, talking out loud. This is how I kind of study, just talk and work through these problems aloud. And I figured I might as well record myself on stream in case other people are interested in hearing that information. I'm just rambling to myself, but over the course of time and through, talking this through and working through it, we can, cross over these humps and really learn this material. So, yeah, it's hopefully this is useful for just learning and stuff, guys. Let's get caught up on the chats. Hunter Script, I think I already said hello, but thank you so much for coming in, Hunter Script. Thank you for the kind message. Flopsy Panda, thank you so much for coming in. He says, how long have you been teaching yourself for? Yeah, I started back at the very end of May, beginning of June of 2024. I started with Harvard CS50P course. My first and only programming I know is in Python, really. I started with the CS50 course. I did it very part-time over the summer of 2024 from June, July to August. In August, at the end of August, I completed and submitted my final project. I have a video on my channel, which is my submission for that final project. It just shows a demo of what it does. It's a inventory storage system for anything, but in my case it was chemical management. And then I started just researching and doing independent study through reading books and various online resources. So I'll pull out my little library here. We started the channel. I read aloud the entire part 1 of the Python Crash Course book by Eric Mays. The part 1 goes over all the fundamentals. I used it as a resolidifying tool for the Python CS50P course. Yes, it does recover a lot of the materials in CS50P, but in my opinion, this did a way, way, way better job of providing you detailed examples and showing how those worked. David Malin in the CS50 course does a good job of getting all of that material into an hour and a half or 2 hours, but this book really does a good job of expanding further on that knowledge. And I also felt that the CS50 course also favored a little bit towards people with programming experience. Now I know that they say it's really for anyone, but I have experience. I've taken calculus in college. I am a scientist for my profession. I am a chemist, a formulation chemist at a biotech company. I have a degree in human biology and a minor in chemistry. And even I found that that course made me want to kind of stop at some points because it got a little bit too long in the lecture, or it started trying to add on too much material too quickly. And I know it's supposed to be at your own pace, but maybe if they could have just broke it down a little bit further, I think that it would have been maybe perfect that way. But obviously, just pause the video and do a little bit slower maybe is the remedy for that. But the Crash Course book does a great job of providing you examples and in-text problems to solve on your own to solidify those. And on my channel, I currently am going back through and posting solution videos to those try-it-yourself problems in the text. So check out those if you want. After this book, or maybe when we start getting towards the end of this book and maybe want some new material, I'm going to start the Fluent Python book. Now I'm very excited to start this one because this will really expand and give us an even deeper, more intermediate to advanced knowledge in Python. Currently, we know, object-oriented programming. We've created a task tracker project which read and saved files, updated those instance attributes via classes for these tasks that I've created, these task objects, and then updated those using datetime module for due date processing for tasks and date modifications and stuff. And so we were able to do that, and then this will just give us an even better push into creating more fluent Pythonic code and give us even more features. So this is going to be a big one that we'll go through. And then lastly, we have so far the Python machine learning book. I'm going to give a shout out to Jeremy from the stream. He is a he's studying machine learning right now. He's getting his master's in it, and he gave me a message with some kind words regarding the stream. So shout out to you, Jeremy. Thanks so much for that, and good luck in your machine learning, and thank you for all your help. I'm sure we will be needing your help when we go over this book in detail. So yeah, if you're wanting to, I have these books, PDF versions, and some of them the ebook versions, linked in the description of, in the Discord, which is in the description below. It's just a free environment that I've created to conglomerate all of my study resources into one location for you guys. And then this stream is just serving as a way for me to expand a skill set, and I already have a profession in chemistry and science, and so this is a stress-free way of learning and coming at this and creating a keeping learning fun is really key. I find that a lot of current people studying computer science are really focused on the financial aspects, the social aspects of the status and title of the job or the environment, and I really wanted to eliminate that and focus directly on the learning and solidifying these concepts and actually understanding them to a deeper level so that I can apply them into not only my profession but into whatever aspects of my life I'm doing. So if that sounds like something you're interested in, sorry for the ramble real fast. I want to just give a shout out to all the new people in here, and yeah, but let's go ahead and let's continue back into this. Thank you so much, you guys, for being here. All right, let's get caught up on the chat. All right. Hopefully that answered your question, Flopsy Panda. That was a long one, sorry. Vance says, n squared plus n log n plus 100 will just be n squared because the others don't matter when you hit big input sizes, I believe. So if you're doing n to the power of 1,000 plus log 1,000 will be like adding 0.09 to 1, 0.00009 to 1, relatively. You can think about big theta as a way to measure, Anas says, you can think about a big theta as a way to measure the time of an algorithm that has no worst case or best case. It kind of has an exact runtime complexity. Interesting. So would you classify a function that has a runtime of theta, or a theta runtime, as something that is fairly predictable in its runtime, like it doesn't vary too much, or it varies so much that it doesn't have, like, it can't be really averaged in a sense, like the data is so skewed? Interesting. I wonder, what do you think about that, Anas? You can, Chris says, You can effectively drop slash ignore the smaller term because it won't impact your worst case time complexity. The smaller term because it won't affect the worst case time complexity. Yeah. N squared is the dominant terms. Others are insignificant as values get large. Vance says you hit 225, by the way, 25 more than yesterday. Awesome. Well, that's dude, that's crazy, you guys. You guys are insane. Like the growth on the channel is really great. I'm thrilled that you guys are enjoying this. It makes it so much easier to get in front of my computer and talk to you guys. Just talk to my screen here. CS50 is goaded. I did CS50X for like 3 weeks and it carried me through the first 2 years of college CS. Yeah, so CS50X is actually republishing a new course that's updated for 2025, and I'm really actually interested in doing it. Do you think it would be beneficial for someone that's maybe already kind of getting past the beginner stages? And now I know I do have a lot to learn for like other languages and things like that. I am strictly focusing on Python for now. I would like to get a solid mastery in it before I move on. I think that that could be very fundamental for things. But yeah, what do you think about the X course and how it would play up to someone that's kind of already taken a few courses and created a few projects? Ryan, thanks so much for leaving a comment. I appreciate you coming in. He says, "How may I ask what your end goal is?" I don't really have an end goal. I really just like learning, honestly. That's I think learning is a privilege in life, and that we should really hold to it. And so I just want to learn as much as I can and take on additional skills and apply them to my life wherever I see fit. And I really enjoy the process of coding. I think it's a very nice, fun mental challenge that is very rewarding when you conquer it or conquer those certain aspects. Ray313 says, "How much do you need to understand data structures and algorithms? Sorry, just starting out." No, you're all good, man. I'm just starting out as well in data structures and algorithms, so this is a great place to be, ask questions, and also to other people in the chat. I myself am learning from people in the chat as well as from this book, and so feel free to follow along with me. Again, I'm not trying. I'm not. My intention for this is I'm not teaching anybody anything. We are peers, you and me. You and me are colleagues, like we would be if we were in class together. I want this to feel like you and me are sitting next to each other in a lecture and we're learning together. I am a beginner, so I should not be, providing advice to people in terms of learning, but I can provide advice from my experiences and what I've done so far. So that's kind of my focus on that. Um, Danny says, "What's your background?" Yeah, I have a Bachelor of Science in Human Biology, and I have a minor in chemistry, and I work as a formulation chemist at a biotech company here in the area I'm at. And I've been doing that for about 3 years. I graduated college at the end of 2021, and I quickly found work after that. The market was nice back then for biotech. Ryan Ray 313. Yeah, I did Calc 1 my freshman year, and I don't remember much, my friend. I wish I did. I wish I remembered a lot more of those concepts, but it was a long time ago. That was almost 6 years, 7 years ago. So time flies. Wow. Ryan says, "Being employed as a web dev is rough. I enjoyed learning stuff like this, but the demand for features doesn't allow much time for deeper learning, to be honest." Ah, that's interesting take. I bet you, like, is it hard to find if you're coding all day in a 9 to 5 environment? Do you find it difficult to want to put in hours outside of work on the same sort of um, you know field? It might be. I can see how it could be easier for me to because I'm in two separate fields, kind of balancing them and learning in a new one. But if you're don't have that distinction, it can maybe have that burnout. Jeremy, you just got a shout out in the chat. The when I was just talking about the books we were going to go over on the channel, I gave you a shout out here. So go back in the stream and check that out. Thanks so much for coming in. Crit says you'll learn how memory works a lot as well, and knowing how memory and pointers work. All right, we are caught up on the chat, you guys. I'm sorry, I just wanted to get caught up and make sure I read everyone's comments and want everybody to feel that they're involved. Um, okay, so we're talking about big theta here, which we have our function here, which is between some constants of c prime and c double prime for our g of n function, our f of n function lies somewhere in the middle for some data set that is greater than the initial indexed value of the data point. So for this example here, we have 3n log n plus 4n plus 5 log n is theta n log n. So why would this be? So I'm guessing that we're trying to find like the middle ground, right? Just by this definition, between these values. So we have an n log n function, we have just a linear function, and we have a log n function. So we know, like, let's go ahead and let's just do this visually, right? I think the best way to see this is visually. So if we have an n log n function, so we have f of n is equal to n log of n, okay? We have f of n is equal to just a linear function, and then we have f of n is equal to just log n, right? So I need to add in the base 2's here for those purposes. It just kind of expands it a little bit. Probably doesn't change it that much, but in theory, we'll just stay consistent. Okay, so we have the n log n function, which has a way faster growth rate than our linear function, which has a faster growth rate than that of our log function. So our log function is the most efficient function, as it can process as inputs get larger, it will result in less time taken for y values. Whereas our linear function lies in the middle here for larger inputs, and our n log n function has a faster growth rate. So y is theta n log n. My initial assumption was that it would have been the linear function, right? Like the middle. But let's see why it's theta n log n instead. So justification. 3n log n is less than or equal to, so we have 3n is less than or equal to 3n log n plus 4n plus 5. So our function, our polynomial, which is less than or equal to our coefficients n log n. Rice for 88, thanks so much for leaving. Yeah, this is Big O Notation. This is my first time ever taking a look at it and learning and trying to go over this myself using you guys and other resources. So thanks so much for joining and leaving a comment. So why is it though that it's n log n and not the linear? Two functions grow at the same rate up to two constant factors. We say that f of n is theta g n. That is real constants. Okay, so let's take this and let's put this into the almighty orb and say, explain why n log n is big theta of this function. Okay, to show why n log n is big theta n log n, right? We need to analyze the asymptotic behavior for each term in the expression and determine which term dominates as n becomes large. Okay? Consider the terms separately. N log n grows faster than n. Yes, as we described, n log n has a faster growth rate. It approaches y infinity faster than the linear function and our logarithmic function. Since the logarithmic terms increase was with n, right? Because you have this n factor outside, multiple. Oh, is it because we have a log n function here and a linear function. So these combined would provide a theta of these. It's kind of almost like a summation in a sense, but not really. Wow, guys, we have 33 people in the stream. This is the biggest it's ever been. So thank you so much for being here. I appreciate you guys joining me tonight. For those that are new here, my name is Michael. I am a college graduate, and I'm 25 years old, just teaching myself after my 9 to 5 and on weekends how to program. Been doing it for about 6 months and started really focusing heavily the past about 2, and making projects and completing online resources and using any sort of methods I can. So thanks so much for joining me. Okay, so n log n grows faster, right? The linear function grows slower than n log n as n increases, and the logarithmic function grows the slowest of all the terms, right? We understand that as the graph here. The asymptotic dominance. When considering the asymptotic complexity, the term that grows the fastest as n increases is the one that will dominate the behavior of the function. Okay, the term n log n grows faster than 4n and 5 log n because n becomes large. The linear term 4n and the logarithmic term 4 and the logarithmic term 5 log n grow slower compared to n log n, and thus they can be considered lower order terms. So big theta notation captures the asymptotic behavior of a function by considering the term that grows the fastest. In this case, n log n dominates the other terms, so n log n plus 4n plus 5 log n equals big theta n log n. So, but I thought that the largest growth rate was the determining factor for big omega functions. I thought that the function with the largest growth rate determines the big omega functions. You're right in saying that the function with the largest growth rate determines big omega, lower bound functions, but let me clarify the relationship between big theta, big O, and big omega notations, and why the growth rate of terms affect these classifications. Big theta notation. Big theta notation describes the tight bound for a function. It provides both an upper and lower bound, meaning it describes how the function behaves asymptotically in both the best and worst case scenarios as n grows large. For function f of n, if g of n is big theta f of n, then f of n grows asymptotically as the same rate of g of n, ignoring constant factors. Big O notation, the upper bound. Big O notation describes the upper bound of a function. It provides the upper limit of how a function grows, meaning that a function will not grow faster than a current rate up to constant factors. Big omega notation describes the lower bound of a function grows, meaning the function will not grow slower than a current rate, again up to constant factors. So let's focus on this function that we're working on here. The largest growth rate is indeed n log n because it increases faster than the linear growth and the logarithmic growth in the polynomial here. The other terms grow slower than n log n, so the context of big theta notation, they become insignificant in the long run as n grows large. To formally say that n log n, we need to show that is bounded by both above and below. Okay, so let's get caught up in the chat here. Chris says you'll learn how memory works a lot well. Strings are just an array of characters, and knowing how memory pointers work is super important for mastering data structures. I'm kind of curious as to how data structures make sense to someone who never learned how memory works. Yeah, we'll get there when we get there, hopefully. This is awesome, man. What do you want to do with this? Hey, Benny, thanks so much for leaving a comment. I really appreciate you joining the chat and joining the channel here. I just like to learn. I think that learning is a, gift, and I want to continue learning as much as I can. I also think that, um, you know, a lot of things taught in our college days can be learned online as well. So I wanted to give that a try. I wanted to see how well I could do teaching myself, and I've always been interested in programming. I have a background in STEM, and so I really wanted to give this a go. Your notes say Big O is the best case. Is it not the best case? Is Big Omega is the lower bound? Yeah. Best case would be the fastest, meaning growing slowly. Okay, it describes the lower bound or the minimum function of the growth rate. This one describes the upper bound or the Can one of you guys try to finish this sentence for me? So the big O notation describes the upper bound or the what growth rate of the function? The maximum growth rate? The upper bound or the uh, Loaded Lou thinks. Thanks so much for leaving a comment and coming in here. I really appreciate you joining. He says, I've never wrote a single line of code, but I'm very interested in learning Python. It's nice to see someone trying. Thank you so much. That's really kind of you. Oh, whoa. Just bumped my thing. That's really kind of you to say. I wish you the best of luck in learning, and feel free to use this channel as a resource in your learning and learn from my mistakes and from my process here. I appreciate you coming in. I feel like I'm going back and forth and in circles trying to define these. I'm getting them flip flop and mixed up, and I really apologize if this is if it's annoying to you guys. But this is the reality of learning these things. Is they're not easy. They're complicated, and they might be easy for a select few number of people, but for the general population, this is just the realistic approach. So yeah. Okay, so while the term with the largest growth rate here influences both big theta and big O notations, big omega describes the lower bound and focuses on how the function grows at least as fast as a certain rate, but it does not necessarily describe the tight bound. For example, this function has a big omega of n because n increases as it grows at least as fast. Because I'm kind of blocked here. For example, the function that we're working on right now is omega of n, big omega of n, because as n increases, right, it grows at least as fast as n. But when you want to describe the exact asymptotic behavior in both upper and lower terms, is the correct notation. The lower bound. So why actually is this omega n? Oh, right. This is not the same function we're looking at. We have log n here. Omega n is right. This is you have n log n plus 4n plus 5 log n is omega n because n as increases, it grows at least as fast as n. Omega of n. Why would it be omega of n if omega, the lower bound or minimum growth rate of a function, determined by the function with the fastest growth rate in the polynomial? So that's not true then. This is not true, right? in this circumstance, why would this have omega n if n log n has a faster growth rate than n? N log n has a faster growth rate than n, but let's clarify the situation, the concept of big omega in more detail. Big omega describes the lower bound. Okay, we've been over this 1,000 times. If we claim that a function f of n is big omega g of n, that means f of n grows at least as fast as g of n for sufficiently large n. However, this does not mean that g of n is the dominant term, only that g of n is the lower limit to f of n. For the n log of n plus 4n plus 5 log of n determines that n log of n dominates the growth because it grows faster than linear and logarithmic. However, because the function includes the term 4n, it is true that n log of n grows at least as fast as n. But why? Why would it grow at least as fast as n if we have a growth factor that is limiting this function? Does that make sense? If we have all three of these functions included in our polynomial, why is our omega the linear function when we have a larger growth rate on our n log n function? Big omega simply states that the function has a minimum growth rate of n. It does not mean that n is the dominant term. It's just a valid lower bound because part of the function grows at a rate or faster. David Baker says, you're getting close. Well, I hope so. I'm trying my best here, guys. Loaded Delu thinks, says, my strong suit isn't really math, and just looking at your screen intimidates me on another level. I don't know how I can start. Please do not feel very this is overwhelming. This might seem very overwhelming to me. It is overwhelming, and to you it is probably will be overwhelming, because if it is to me, then it definitely is. But there's levels to these things. I've been reading this book every day for the past week, right? I've been slowly building up to this, so you can't expect yourself to join the stream, today and then expect to pick up on this if you've never seen it before. We've been grinding away at this for the past few weeks or days here, the past weeks, and it's a process. It's not an overnight thing. So, and I think that's where a lot of people struggle is they think it's an overnight thing and they try to do too much and then they burn out. So don't burn out. You got this. Because f of n is the main function. F of n has to be able to accommodate all within. So that's why they have a semester long worth of lectures for DSA instead of a quick lecture, because it takes time. Yeah, definitely. I just don't get. I think my brain is trying to come up with some sort of definition for figuring this out, like a statement that I can rely on to look back on to determine what is big O for this. What is is there like a blanket statement, kind of like this, but this, it's not, big omega is not determined by the function with the fastest growth rate in the polynomial from what I've seen, right? That's not the case. Okay, let's keep moving here, guys. Comparative analysis. Suppose two algorithms solving the same problem are available. an algorithm A, which is running at time O of n, big O of n, and an algorithm B, which is running at a time big O of n squared. So right off the bat, what we know from our previous knowledge is that this function, linear function, big O of n, is faster and more efficient than the function big O of n squared. We know that big O of n has a slower growth rate than big O of n squared, meaning that as input values n approach infinity, big O of n will output values that are smaller over time than this function. Which algorithm is better? We know that n is big O of n squared, which implies that algorithm A is asymptotically better than algorithm B, although for a small value of n, B may have a lower running time than A. Right, so if we go back to that graph, right, where we have a linear function and instead of let's put in no, what was it? Sorry. Yeah, and squared. Right? So for relatively small values, it might provide, or small inputs, it might provide faster, you know, it might provide faster or better response. But as we increase, we are going to get less and less efficient because we're approaching an asymptotic behavior here on the geometric or the quadratic function, right? Loaded Lou says, "How often are you live teaching yourself?" Yeah, I stream pretty much almost every day. For the past week, I have been after my 9 to 5 job. I stream. I try to get on around 7 p.m. Today I got on around 6 because I got off a little bit early today. But I try to get on about 7 p.m. and go till around 9 or 9:30. Okay, right. We can use the big O notation to order classes of functions by asymptotic growth rate. Our 7 functions are ordered by increasing growth rate in the following sequences. That is, if a function f of n precedes a function g of n in the sequence f of n is big O g of n. So basically it's saying that we have it like in our notes, it gave us these, we have a constant function, we have a logarithmic function, we have a linear function, we have an n log n function, we have a quadratic function, we have a cubic function, and we have an exponential function. And as we go from left to right, our growth rates on these functions increase, causing our functions to become less efficient and asymptotically worse as we go from left to right. Yeah, Chris, I don't think a link was sent. I don't think, maybe you're not allowed to post links in the chat or something. I'm not sure if that's a feature or not. Feel free to load it up in the Discord though, if you're in the Discord. So we illustrate the growth rates of the 7 functions in figure 3.2, table 3.2. So right, for n input values, as you can see, as we go from right to left, or left to right, I'm sorry, these output values increase quite drastically for large sets of data. We further illustrate the importance of the asymptotic viewpoint in table 3.3. This table explores the maximum size allowed for an input instance that is preceded by an algorithm in 1 second, 1 minute, and 1 hour. It shows the importance of good algorithm design because an asymptotically slow algorithm is beaten in the long run by a asymptotically faster algorithm, even if the constant factor for the asymptotically faster algorithm is worse. So in the long run, even if you have a constant factor for the number of primitive operations that is worse in your faster asymptotically favorable algorithm, it'll still beat your slower one. So in terms of 400, um, running time, as you can see, as n increases running time, we just have that same kind of behavior happening. All right. O of n is the quote unquote converge in higher inputs. Omega n is the minimum it will be in higher inputs. And theta n is the tight bound in high inputs. Is the converge. What do you mean by converge? Like O of n is the quote unquote converge in higher inputs. Okay. Aiden Seal says, what is the code application you're using? I like how the terminal is presented. Yeah, this is just VS Code, Microsoft's VS Code. And then I'm just using a TXT file, so just a regular text file to take notes within my DSA repo here. All right, I'll definitely be back another day. Wish you luck. Thanks so much for coming in. I appreciate you stopping in with the time you had. Anytime you can come and join me. I know time is valuable, so I really appreciate you coming in here and spending some learning with me. It's really great. And I'll see you another time. Distracted Funny. Hey, this is my first time watching you. Love seeing people enjoy learning on their own. Join the Discord, by the way. I wish to learn CS as well. I'm in university right now getting my CS degree. That's really awesome. That's really takes a lot of, effort, and you should be proud that you're in college getting a CS degree. And I hope everything goes well. Good luck to you. Thanks so much for joining the channel and the Discord. I look forward to interacting with you more and networking with you. Roith, sorry if I pronounced that wrong. Hey, great work. Keep going. By the way, any plans on pushing your learning notes to GitHub? Yeah, I can push these to GitHub at any time. If you guys would want them, let me know and I'll push them tonight. I really don't care. I can keep a running a kind of open source note for everybody to access if they would like. But yeah. I think I wrote converge in my notes back then because I was taking Calc 3 and made some sort of connection for myself. But basically, the O of n line, the n squared the n squared graph will dominate it. Got you. Okay. The importance of good algorithm design goes beyond just what can be solved effectively on a given computer. However, as shown in Table 3.4, even if we achieve a dramatic speedup in hardware, we still cannot overcome the handicap of an asymptotically slow algorithm. This table shows the new maximum problem size achievable. This table shows the new maximum problem size achievable for any fixed amount of time assuming algorithms with the number of running times are now run on a computer 256 times faster than the previous one. Increase in the maximum size of a problem that can be solved in a fixed amount of time by using a computer that's... So you have a running time, a linear running time, quadratic running time, and an exponential running time. Interesting. All right. I'm gonna be honest. I didn't take any notes for chapter 2 or 1. Chapter 2 and 1 was all about. Chapter 1 was heavily about Python review. So I didn't feel like I kind of really went through that rather quickly. I didn't stop and take notes and kind of grind through it. A lot of it was review, like I said. And then chapter 2, I did not take notes in either. But chapter 2, I started, I think, but I didn't really do anything. Sorry, let me see here. Yeah, I didn't really do anything. The chapter 2 just gives like a brief overview of classes in Python and reviewing classes and the dunder methods associated with classes for operator overloading and things like that. But I started taking notes in chapter 3 because this is where we kind of really introduced new materials. And so, yeah, I will go ahead and push this to GitHub so everybody can have access. And yeah, that'd be great. That's a good idea. Okay, some words of caution. A few words of caution about asymptotic notation are in order at this point. First, note that the use of the big O and related notations can be somewhat misleading should the constant factors they quote unquote hide be very large. For example, while it is true that a function 10 to the power of 100 n times n is big O of n, right? Because we're looking for the upper bound. Um, if this is the running time of an algorithm being compared to those whose running time is 10 n log n, we should prefer the big O of n log n time algorithm, even though the linear time algorithm is asymptotically faster. This preference is because the constant factor of 10 to the power of 100, right? So as we talked about earlier, is when we provide this big O notation or this asymptotic analysis notation and things like that, we choose to leave off the C or constant value. Now, what does the C or constant value represent? Well, that just represents the number of primitive operations that the function or algorithm essentially has. Now, what are primitive operations? Well, these are just things that the coding language can perform, like basic math, addition, subtraction, comparisons, less than or equal to, accessing data within certain elements, control flows such as looping, or just basic function calls. So you can, like we talked about at the beginning of the chapter, you can kind of count up these primitive operations to determine speed. And then if you're iterating over some sort of data set or manipulating data sets, then you apply like an n value to these primitive operations and determine based on these primitive operations, like if you have loops or comparisons or things along those lines, determine the time complexity associated with this asymptotic analysis. If you have, like we talked about, nested for loops, right? When we talked about like the logarithmic function or right here, quadratic function, right? Where you have a function when given an input value of n, the function assigns the product of itself, so just n squared. The algorithms have nested loops where the inner loop performs a linear number of operations and the outer loop is performing a linear number of operations, right? So we for I in the range of n, and then for j in the range of n as well, right? We're performing an iteration over n 2 times, thus n squared for the quadratic function. So these primitive operations, when used in various orders or in terms of coding, determine these functions and how they interact. And so it's really interesting to understand how someone kind of figured this out and took coding. Obviously, coding and programming has always been kind of math-based, but really applied these asymptotic relationships to these functions. It's like you have functions in coding which are just programs, but then you have mathematical functions. So it's really quite interesting how closely they intertwine and relate. It's probably often why you see so many math majors in college are forced to take programming classes as well, like a Python course or like a statistics and math computer science course or something like that because of the crossover that they have. Um, and I wish I would have known programming from my calculus class because you could use for loops to literally calculate calculus problems for you. You can house variables and then use for loops to sum and iterate over like data sets, which is basically calculus, right? For n in certain ranges, do these calculus values. So it's really interesting. Okay, so words of caution, right? If you have constant values that end up being so large, they can actually end up overriding the time complexity elements found within just the basic function, structure. All right, so this preference is because the constant factor 10 to the power of 100, which is called 1 googol, is believed by many astronomers to be an upper bound on the number of atoms in the observed universe. So we are unlikely to ever have a real world problem that has this number as its input size. Thus, even when using big O notation, we should at least be somewhat mindful of the constant factors and lower order terms we are quote unquote hiding in the big O notation. The observation above raises the issue of what constitutes a quote unquote fast algorithm. Generally speaking, any algorithm running in O n log n time with a reasonable constant factor should be considered efficient. Even an big O of n squared, or a quadratic function may be fast enough in some contexts. That is, when n is small, so when we have small input values going into our function, so a small list of integers, but that is when n is small. But an algorithm running in big O of n squared, a quadratic function, should almost never be considered efficient. A exponential function should almost never be considered efficient. Exponential running times. There's a famous story about the inventor of the game of chess. He asked only his king to pay him 1 grain of rice for the first square on the board, 2 grains of rice for the second, 4 grains for the third, 8 for the fourth, and so on. It is an interesting test of programming skills to write a program to compute exactly the number of grains the king would have to pay. Oh, that's interesting. 2, 4, 8. So you basically use kind of like a recursion method here, essentially to exponentially. This is like when they tell you, would you rather have a dollar a day or like a penny an hour, right? Or something like that. It's kind of like those problems where exponential times it really ramps up faster than you really think it does. Like the snowball effect in the stock market, like it's the same kind of general principle. As I think people don't really understand how fast exponential functions drastically ramp up for runtime or for growth rate. If we must draw a line between efficient and inefficient algorithms, therefore it is natural to make this distinction, be that between those algorithms running in polynomial time and those running in exponential time. We must draw a line between efficient and inefficient algorithms. Therefore, it is natural to make this distinction and be that between those algorithms running in polynomial time and those running in exponential time. That is, make the distinction between algorithms with a runtime that is exponential for some constant c, and those with a runtime. That is, make the distinction between algorithms with a runtime where the constant value is the exponent, whereas and those with a running time that is big O of exponential running time for some constant b greater than 1. Like so many notations we have discussed in this section, this too should be taken with a grain of salt for an algorithm running in big O n to the 100th power. So time should probably not be considered efficient. Even so, the distinction between polynomial time and exponential time algorithms is considered a robust measure of traceability or tractability. Okay, so it tried to preface us that, there are edge cases where if you apply large exponents to, quadratic functions or exponential function, quadratic functions, or you apply, large base values to exponential functions, that they may have some like overlap in terms of their efficiency with other. It's just the constant can change things for sure if large enough. All right. Okay, let's go ahead and catch up with the chat here. I appreciate you coming. Those that are new, my name is Michael. Graduated back in 2021 with a degree in human biology and a minor in chemistry. I work as a formulation chemist for a biotech company making biological controls for inpatient diagnostics. I wanted to learn to program because I found many instances in my current work and profession where I have to manually calculate a lot of chemical matrices using, tables and things like that, and just basic intuition, kind of seeing where numbers fall and where they would predictably potentially fall if included in the matrix. And I thought what would be a cool way to have a computer do this for me. And although I haven't solved that problem yet, I still do the matrix by hand. I actually made one a couple of days ago by hand. I I I've just kind of been bit by the bug of programming, and I've continued to learn and really like the process of it. And so, if you find this interesting to you, feel free to follow along to the channel. We've been growing quite rapidly over the past couple of days and the past week. We're crossed over 225 subs, which is crazy. I can't believe you guys are. Well, obviously, my hope and goal was you guys would enjoy this, and I can't believe it's actually working out. Pardon me, but let's continue here for examples. Or sorry, we have some chats here. Um, Tenzin Dayab says, "What are your other tabs?" Yeah, so at the end of every chapter, they provide you a bunch of practice problems. And so I go ahead and go through these live on stream and complete these. So in our chapter 2, these were all the practice problems we completed. They're pretty detailed. We, created we used the credit card class provided. We, you know, did all these, we created instances of this class. We appended them to a wallet, and then we iterated over the wallet. Um, or we added charges and stuff. So it has all these practice problems which help to re-solidify those concepts learned in the chapter. They have reinforcement problems, creativity problems, and then project problems. But I only do the reinforcement problems. I feel like those are enough for the concepts. And so when we get to the end of chapter 3, we'll go ahead and work on the chapter 3 problems. But yeah, these are just the problems from chapter 2 that we worked on previously. And I'm currently just taking notes. The book author name, a dig, I am not exactly sure. Let me go ahead and let's look it up. I need to know it. I feel like it's important. Data structures, and algorithms in Python. It's by Michael Goodrich and Roberto Tomasia and Michael Goldwasser. So, a couple of Michaels. Also, where you're learning this from, some PDF online, and is it free? Yeah, this is Data Structures and Algorithms by those authors that I just listed. This is a PDF I found online of the book. The physical text costs like over $100, and so I usually like getting the physical text and stuff, but I decided to do this one on the budget. So we're doing the PDF, and I just also have a Discord link below where I provide a conglomerate of all my study resources from CS50P with the proper links to how to work that, Python crash course, Fluent Python, everything like that. Yeah. Yeah, this is the book right here. Has like a brown reddish cover. Okay. All right, let's keep it moving here, you guys. Examples of an algorithm analysis. So now that we have the big O notation for doing algorithm analysis, let's give some examples by characterizing the running time of some simple algorithms using this notation. Moreover, in keeping with our earlier promise, we will illustrate below how each of these 7 functions given earlier in this chapter can be used to characterize the running time of an example algorithm. Rather than using pseudocode in this section, we give complete Python implementations for our examples. So this is what's nice about this book, is that it will give you complete Python code as examples. We use Python's list class as the natural representation for any quote-unquote array of values. In Chapter 5, we will fully explore the underpinnings of the Python's list class and the efficiencies of the various behaviors that it supports. In this section, we rely on just a few of its behaviors, discussing their efficiencies as introduced. Time constant operations. Given an instance named data of the Python's list class, a call to the function length data is evaluated in constant time. This is a very simple algorithm because the list class maintains for each list an instance variable that records the current length of the list. This is a very simple algorithm because the list class maintains for each list an instance variable that records the length of the list, okay? This allows it to immediately report that length rather than taking time to iteratively count each of the elements in the list. Using asymptotic notation, we can say that this function runs in O of 1 time. That is, the function time of this function is independent of the length n of the list, right? So basically this says is we have a class in our Python, right, called list, which is used to create the list like in the arrays in Python. Now, based on our knowledge of classes, we know that classes have instance variables. And inside one of those instance variables, which basically just house attributes associated with those objects. For instance, if I had an object of a house, an instance variable for the object of a house could be red door, right? Or door, and it could be equal to red. Or an instance variable could be level, right, for the house, and the level could be, or stories, sorry, let's do stories. It could be for a single story house, it could be 1 for the value. For the instance variable stories for a double story house, it could be 2, right? So these instance variables are just attributes. Now think of like a human, right? If I have an object of a human, if me, Michael, is an object, don't treat me like an object. If Michael or a human, I create objects and I create me, Michael object, well, an attribute could be eyes, right? Every human that's created, hopefully, hopefully for them, have eyes in normal circumstances. Now, the value associated with eyes could represent the color. So for my instance variable, from the object Michael, eyes could be for the self.eyes instance variable, self meaning the current object me, would be blue. For someone else, it could be brown. So these are just associated attributes. So the list class in Python has a attribute which just houses the actual length of the data provided to the list class. The houses the length of the object list in the list class. So it can then just be directly called forward by the user, such as like print self._length of this object, or self.length of this object for the instance variable, and called directly rather than having to iterate throughout the data set at that point as well. So just like you would have to if you had external data imported into Python or something like that. So another central behavior of Python's list class is that it allows access to an arbitrary element in the list using syntax data at index for integer index j. Because Python's lists are implemented as array-based sequences, references to list elements are sorted in a consecutive block of memory. The jth element of the list can be found not by iterating through the list one element at a time, but by validating the index and using it as an offset into the underlying array. In turn, computer hardware supports constant time access to an element based on its memory address. Therefore, we say that the expression data at index j is evaluated in O of 1 time for Python's list. Okay, so providing the length of a list is in O of 1 time, and accessing a data point at a certain index is also in O of 1 time, just because of the hardware support provided by computers to store the array using its array in memory, I think. Okay. Is that how that works? Is that your computer uses its onboard memory to actually house that data, and so you can just directly call that from the computer's hardware memory or random access memory, and so it is just constant time. There's no iterating. Joshua Cleveland, thanks so much for joining the chat and leaving a comment. I appreciate you coming in. My name is Michael, and I'm glad you're here. Yeah, this is Data Structures and Algorithms in Python. This is a book by Michael Goodrich and some other authors. Um, I provide a PDF in my Discord below, which is just a free conglomerate of all of my study resources. Also, you can just Google this online and find it online. But yeah, I just read through this and am completing the books at the end of the problems at the end of the chapter. So thanks so much for being here. Okay. Revisiting the problem and finding the maximum of a sequence. Okay, so if you remember earlier, we had a problem where we iterated through n data sets and found the maximum of the n data sets, kind of like the Python's max function, but we just implemented our own. So for our next example, we revisit the find_max algorithm. Given code fragment 3.1 on page 123 for finding the largest value in a sequence. Prop 3.7 on page 125 claimed an O of n runtime for the find max algorithm. Consistent with our early analysis of syntax data at index 0, the initialization uses O of 1 time. The loop executes n times, and within each iteration it performs one comparison and possibly one assignment statement, as well as maintenance of the loop variable. Finally, we note that the mechanism for enacting a return statement in Python uses O of 1 time. Combining these steps, we have the find max function runs in O of n time. Okay, so if I go back to page 123 to show you guys this, well, we're kind of moving quick here. We're getting past 123. Okay, so we have this find max function that we were provided earlier. This is very similar to the max function provided in Python itself. We just have our own written example here. So all it does is just returns the maximum element found in the list. So if we have an element with numbers 1, 2, 3, 4, and 5, it will return number 5, or because it's the largest. So basically all this does is when we call the function and provide it some sort of data set within the function, it assigns the first index value of that data set as the biggest value, right? By default, just off of thinking off our own head, if we start a list, if we start from nothing and we start in the first place, well, that first number is our maximum number so far. We only have seen one number, so by default, it's our maximum number. Now, when we get to the second number, we will need to compare that number to the previous number and do an evaluation. Is this bigger? Is it less? If it's bigger, let's override. If it's less, let's move on to the next, right? So we assign that first value in our list as the biggest, and then we say for every value in the data set, if that value that we are currently on and selected is bigger than or is greater than the quote-unquote biggest variable, which houses the first data point. So if the second data point is bigger than the first, then we're going to reassign biggest as that value, and we will return biggest. And it's not said in here, but by default, else it would just continue looping through this loop until the loop is complete and it returns that biggest value. Now, if by chance the biggest value was the first value found and it never actually updated this line of code for a new value, it would just return data at index value 0. So very simple function going on here, but what it's trying to say is now we're trying to evaluate the time complexity of this function. Now we know that that functions and just basic kind of code typically has primitive operations. Primitive operations or primitive operators are just basic, functions or operations that happen in code, in terms of just, actually writing code. So by doing any, pardon me, by doing math or by doing comparisons, like this is a comparison right here, right? By doing data access, right? We're accessing a data point right here, right? Control flow, we're looping, right? We're doing a loop, we're controlling the flow of this program. We're manipulating, or we're saying you need to do this over and over again until you get some value. And then function calls, right? Just the overall find max function call. So these are all examples of primitive operators. Now, we know that just by that definition it provided that by indexing or accessing data points, assigning them to variables, evaluating conditions based on magnitude, and assigning values and also returning values all have a constant time of big O. So if we had just a function that just assigned a value, that would have a big O of 1 time, meaning that it has a constant time. Um, Rather, now, but we are introducing a variable in we are introducing a data set into here, and we are iterating over that data set, right? So this kind of brings up that topic we talked about with the quadratic function where we have nested for loops, but we don't have a nested for loop in this case, we just have one. So we can kind of right off the bat infer or deduce that this is not a quadratic based time complexity. We only have one for loop. Um, we're not evaluating n over and over again and iterating over n multiple times. Now, so we have one for loop, so just based off that definition, we are evaluating the data set or iterating through it one time. So our time complexity at that point would be equal to n, right? It is dependent upon all of the values in our data set. We have to loop over, we will, according to this function, loop over every single value in our data set for value in data, right? If value is equal to biggest, return biggest. We don't have a catch saying to stop the for loop and or like a while loop and saying break or something. We're going to iterate all the way through. Now, probably just having a for loop creates that complexity no matter what, but even if you do break, but that might be beside the point. So, right, just based off this for loop, we're iterating through the data set, we're going to have a time complexity now equal to f of n is equal to n, or big O of n. We don't have any other for loops taking place. We just have conditionals happening, which have a time complexity of 1, and we have a return that also has a time complexity of 1. So this function would overall have a time complexity of big O of n. The constant function is overridden by the slower function provided, or the worst case scenario function given. The function will run on the worst case scenario in big O of n time. It is bottlenecked by the big O of n. In the best case scenario, yeah, gotcha. Cool. Cool. That helps explain it. Now, talking through that, hopefully that helps explain things that we're learning here. So let's go back down here. Okay, cool. So, right, combining these steps, we have to find the maximum function runs in O of n time. Further analysis of the maximum finding algorithm. A more interesting question about find max function is how many times we might update the current biggest values, right? If just by nature of the array is if every sequential value has n plus 1, if that actually, if n gets bigger itself, so for example, we have a list of 1, 2, 3, 4, 5, well, on each instance of our recursion through the list, or our iteration, through the list, we will be assigning biggest as, or overriding biggest for that value. Now, this essentially increases the amount of constant or primitive operations that our function will be doing. So we do have to take that into account. Okay, so we don't know how many times I might update the biggest value. In the worst case scenario, if the data is given us in increasing order, the biggest value is reassigned n minus 1 times. But if the input is given us in random order with all orders equally likely, what would be the expected number of times we update the biggest value in this case? Okay, let's try to answer this question without going on. So just like we said earlier, if every number causes an update to if every number in our array causes an update to the biggest variable in our find max function, right? The actual biggest value will be reassigned n minus 1 times, right? You'll do one less than the total amount of n because you'll end on that last value. You won't have to move on anymore. You'll be at the biggest. But what if it's given us in random order? So what if we get a list with 5, with 3, with 2? Well, at that point, you could stop at either the beginning of the list, you could stop at the end of the list, or you could assign at the end of the list, or you could essentially assign at any point in the list. It's just completely random. To answer this question, note that we update the current biggest value in an iteration of the loop only if the current element is bigger than all the elements that precede it, right? So if we're on element 5, we only update on element 5 if element 5 happens to be less than all the, we only know that if element 5 is updated, we know that it is greater than elements index 0 to 4 through 4, right? If the sequence is given to us in random order, the probability that the jth element or the indexed element is the largest of the first j elements is 1 divided by j, assuming uniqueness, 1 over j. Hence, the expected number of times we update the biggest, including initialization, is h of n is equal to the sum from j is 1 all the way to n, 1 divided by j, which is known as the nth harmonic number. It turns out, see prop b.16, that h sub n is big O of n log n. You're summing for all the values in n, and then you're recursing, or so you're iterating through 1 to n, but you're also applying a mathematical operation at every instance of n. So no, it's not n log n, it's log n, because why would it be log n? It turns out, see prop b.16, where's prop b.16? I'll have to find it. Therefore, the expected number of times the biggest value is updated by find max or a randomly ordered sequence is O of log n. Okay, this is interesting. So if we have some function, right, h of n, which is equal to, for all the values, sum all of the values from j equals 1 all the way up to n. No, sum all the values up to n for when starting at j equals 1. So you'll do 1 divided by 1, which is 1, plus 1 divided by 2, plus 1 divided by 3, all the way through n, and return that sum. So why is it log n though? So we know that a linear function is proportional to n. We know that a constant function has no relation to n, but the logarithmic function determines the number of steps needed to reduce the base down, not the base, the exponent to 1, n down to 1, right? So this is log base 2n, interesting. So I'm gonna look this up and say why the harmonic number is O log n because its growth rate is asymptotically similar to the natural logarithm of n. Here's the reasoning. Definition of h sub n. The nth harmonic number is 1 plus, 1 divided by 2, 1 divided by 3, whatever, all the way through 1 to n. Relation to the natural logarithm. The harmonic number h sub n is approximately related to the natural logarithm of n via the following asymptotic formula. H sub n is about equal to the natural log of n plus gamma. Is that gamma? Where, no, that's not gamma. That's, I forgot what that's called. Dang it. In asymptotic notation, h sub n is big O log n if there exists a constant c such that c log n for all instances large n. Since a is approximately explain it in more simple terms. Sure. So the harmonic number grows slowly as n gets bigger, right? It turns out that this growth is similar to the growth of log n. Why is that? The first few terms look like this, add a lot, and therefore the terms adds very little. So the growth slower and slower the more terms you add. Okay, yeah. So the more n values, the larger your n value, the less amount you're adding towards the end, right? Or yeah. Why log n? In math, O log n means the growth rate is at most like log n. Since h and n and log n grow about the same speed, okay, so we're kind of just visually saying that these two have similar or proportionally grow at the same speed, have a growth rate, so it can be encompassed in that category. Now, is it exact? I'm not sure, but it has a similar relationship, ratio-wise probably. Okay. Prefix averages. The next problem we consider is computing what are known as prefix averages of a sequence of numbers. Namely, given a sequence S consisting of n numbers, so we have a sequence S with some amount of numbers, we want to compute a sequence A such that A at index j is the average of elements of S to 0 all the way to S sub j for j equals 0 up to n minus 1, all the way through n minus 1. So we're trying to find at some point in our we have a sequence of numbers, right? We have an array, and we want to compute a new sequence that, given at some index value of j, we want to at sequence of index value j, we want to sum up all the values, or the average of all the values from sequence 0 to sequence j. Okay, gotcha. Computing prefix averages has many applications in economics and statistics. For example, given the year-by-year returns of a mutual fund ordered from recent to past, an investor will typically want to see the fund's average annual returns for the most recent year, the most recent 3 years, the most recent 5 years, and so on. Likewise, given a stream of daily web usage logs, the website manager may wish to track average usage trends over various time periods. We analyzed 3 different implementations that solve this problem, but with rather differing running times. Okay, this is trying to give you some kind of like it's kind of giving you some information here that I don't feel it's super necessary, but interesting. Time is 8:38. Wow, I'm grinding away here, people. Check my phone here. Okay, we're all right. I appreciate you guys joining me this evening. My name is Michael. I'm a independent learner of computer science, teaching myself through various online resources. I created this channel as a way for others in a similar situation to maybe gain inspiration or motivation through my, grinding away here at learning this. I have a background in human biology. I have a Bachelor of Science in Human Biology and a minor in chemistry, and I work as a formulation chemist at a biotech company. And I'm just trying to learn new skills in coding. So if this is something that you're interested in or in a similar situation, feel free to follow along to the channel. We've been growing at a great rate the past few days to weeks, and yeah, I can't wait to see what the future holds for the channel and for our progress here in programming. Okay, so we have a quadratic time algorithm. Our first algorithm for computing prefix averages, named prefix average 1, is shown in code fragment 3.2. It computes every element A separately using an inner loop to compute the partial sum. Okay, so we are given some sequence and we're going to run prefix average on it. So we have n, which is just the length of a sequence. We have A, which is a list with a zero in it, times n elements. So we're going to create a new list of zeros up to n elements. So if n equals 5, right, we'll have a length of 5 provided. We'll have 5 zeros provided in our A list. So this is creating just a template list to store our values in. So for j in the range n, so we're getting the index value in the range of n, right? The range of our sequence. Total is equal to 0, so we're creating a counter here. And then we have a nested loop inside of here. So remember from our discussion earlier, when we have two loops within each other, we are in a quadratic function, right? We're iterating over our data or our sequence twice over, right? One time for a linear, two times for a quadratic. So we get the index value of our sequence. We save those index values, and then for integer in the range of j plus 1, for integer for I in range of 0 to j plus 1, so j So this is creating the actual sequence from j up to. So if you remember from this problem here, right, we go from sequence 0 all the way to sequence of index of j, right? So we're creating a range from 0 all the way to j plus 1. So we're including the last value of j here. And then we're going to do total. We're going to increase total by the sequence value at index I, right here, at that point I, at that integer. And then we're going to within that loop take our list A at index value j. Total is equal to j plus 1. Interesting. Okay, in order to analyze the prefix average algorithm, we consider the various steps that are executed. The statement n equals length s executes in constant time as described in the beginning of section 3.3.3. So this is constant, right? The length is saved in memory on the hardware system and is called back in an instance variable from the list class. The statement a equals 0 times n, list 0 times n, causes the creation and initialization of a Python list with the length n, and all entries are equal to 0. This uses the constant number of primitive operations per element and thus runs in O of n time. Right? We're using n here and we're multiplying it by some value, so we are in O of n time. So we have a constant time and we have an O of n time. So far this algorithm is running in O of n time. There are two nested for loops which are controlled retrospectively by a counter counters j and I. The body of the outer loop controlled by counter j is executed n times for j equals 0 all the way to n minus 1. Therefore, statements total equals 0 and list A at index point at index j is equal to total executed n times each. This implies that these two statements plus the management of counter j in the range contribute to a number of primitive operations proportional to n, that is O of n time. The body of the inner loop, which is controlled by counter I, is executed j plus 1 times, depending on the current value of the outer loop j, counter j. Thus, statement total plus or equals the sequence at index I in the inner loop is executed 1 plus 3 plus 1 plus 2 plus 3 all the way to n times. By recalling prop 3.3, we know that 1 plus 3, 2 plus 3 all the way to n is equal to n times n plus 1 divided by 2, which implies that the statement in the inner loop contributes to O of n times squared, O of n squared time. A similar argument can be done for the primitive operations associated with maintaining a counter, which is also O of n time. Joseph says, the only thing I hate in math is coding. Well, I think I might be the opposite. I like the coding aspect of it. I don't like all the I think it gets kind of annoying, like all this dot note, all the notation and stuff. I think in math is a little bit more annoying and harder to follow. But to each their own. I appreciate you coming in, Joseph, and leaving a comment. Thanks so much for being here. So yeah, remember, like we have two nested loops here, so this is going to be an O of n squared time. The running time of implementation prefix average 1 is given by the sum of three terms. The first and the second terms are O of n, and the third is O of n squared. By a simple application of prop 3.9, the running time of prefix average 1 is O of n squared. Where's 3.9? I want to see that. 3.7. Table. Okay. So this is prop 3.9, which says if f of n is a polynomial of d degree, that is, we have a polynomial all the way up to d degree. Okay, yeah. Okay, cool. Okay, we're on page 132. How long do we have left in this chapter? Jeez. Oh, we're almost done. We're less than 10 pages away, you guys. We're almost there. Oh my gosh, this has been a long one. A lot of information in this chapter, a lot of learning, but this is all very crucial and necessary stuff for algorithm analysis and programming. So we're on page 132 right now, and we are almost, and 141 is the last page of the chapter. So we're almost there, you guys. So bear with me here. Stay with me. But I got about 10 minutes left in today's stream, and then I'm going to call it for today. So I appreciate you joining in with me today. We'll stay together for the last 10 minutes. I know I have been extremely slacking in continuing on with my personal projects, such as the small business manager that we've been working on, which is essentially, for those that don't know what that project is we're working on, I'm creating an object-oriented script that will take in items for like a small business or like a selling platform. Those items can then be converted from items into for sale items and then sold items via child classes from the item class parent base class. And these items then can be added into an inventory data center or a data structure in the form of a list that gets added into a form of a dictionary, and then these hopefully that's kind of how I have it right now, where I read and write the files and I can add in those associated items for the small business manager. But I want to create a way to convert those items. I can make the sales, make the transactions, like in terms of tracking a database, and then um, develop, business reports such as like financial statements, income statements, cost of goods statements, like all those kind of general small business tax reports that are needed that maybe people don't know how to do or um, are lack experience with. We can create a program that will a take and track all their inventory, and then b um, process all that inventory into a general formal reports that can be filtered for various time constraints and various criteria along those lines. So it's kind of going to use a lot of the mechanisms used in my Python CS50P course I did, offered through Harvard online and EDX. I created an inventory management system, and then I recently published and pushed to my GitHub a task tracker application. So please go check that out if you're interested in it, where you can load tasks. Those tasks are saved on files and read back when you re-enter the program. Those tasks are assigned due dates in the future, such as if I have a task I enter, such as mow the lawn, it would be, and I give it 5 days to complete, it would auto generate a due date 5 days from the current day I made the task using the date time module. And if I were to go ahead and exit out of the program, a couple days pass and reopen the program, those tasks that were previously loaded in the program are read on the file, loaded into the system, and then edit and updated for that future criteria and condition, because that due date is now closer in time than it was a couple days ago. And so that was really fun and interesting. We wrote that whole application live on stream here. And so we do everything, and all of our learning is completely transparent. I really try not to do any learning that's not on stream. I work a 9 to 5, so I don't have a lot of time during the day to do any external learning. I will maybe like watch some videos to refresh and solidify concepts I did learn on stream, but I want to keep this completely transparent for you guys. And as a beginner myself, I think it's very useful, and it could be very useful for other beginners to use this as maybe not a template really, because I don't want people to be learning from what I'm saying, but rather taking in what I say with a grain of salt and learning on their own with that information. And so this might just provide as a structure or a way to show that maybe it is possible to teach yourself. And for the most part, we are kind of proving that it is possible, and we're doing our best to understand these concepts. And like I said, guys, it's a long haul. It's a huge umbrella, a mass amount of material. People go to college and study this for 4 years. They go to master's programs and study this for an additional 2. And even then, they still don't know all the concepts, or aren't super, uh, you know, they don't have all the information. They still have to continue to learn. So we are at a uphill battle for sure, but I am charging forward. I'm not scared of it. I'm having a lot of fun doing it. And if you're also in the same situation as me, feel free to follow along. I love connecting and talking to you guys and interacting. Feel free to join the Discord in the link below, where I will be posting just the conglomerate of all my resources into one central location. And then, maybe we can create like an open source project for the Discord members. I think I'm also going to post private videos for my CS50P problem set solutions. I know that they don't like public sharing of those answers, but I think it is very important and vital, and could be useful to learn from other people's um, solutions. Obviously, you don't want to just copy and paste, but you want to evaluate and go through and understand why that programmer wrote those solutions the way they did. And so I'm going to publish some private videos just for the Discord members. Um, it's all completely free. Again, I would never charge for this. I am a beginner. I'm not going to charge for something that I don't know anything really about, in the general scheme of things. I appreciate you guys joining me today. Feel free to follow along. I'll be here back tomorrow at around 6 or 7 p.m. All the way until about 9:30. And yeah, and I promise you guys we are going to jump back onto the projects. Actually, I want to get through this chapter 3 while things are still fresh. We only have about 10 pages left, and then we can start chipping away at the problems at the end of the chapter, and then into the projects like we have been in the past. But this weekend we will be streaming for 4 or 5 hours, 6 hours maybe. I might even do 2 sessions, like a morning and an afternoon and an evening session, where in the morning I'll do learning, and then the afternoon I'll do practice and working on the projects. Whatever. I really enjoy this. This is one of my few hobbies, and If that's something that's interesting to you, please follow along. I know I'm kind of rambling here, but yeah, thank you so much for tuning in today, guys. I'm going to call it here for today. We did a lot. We really refreshed the functions here, right? We have a let's just quickly we have a constant function which is completely independent upon the input size that the user provides or whoever provides. The function will always output a value of c. These are like basic fundamental operations such as these primitive operations, math, comparisons, data access, control flow. We have a logarithm function which essentially logarithms uh, just reduce your data sample, your input value by the base, and then output a value of how many times it took to recursively reduce that base by or reduce that input value by the base. So with a base 2, we are having the input value over and over again, and the output is how many halves do we create. And so if we have a n of 8 and we have a base of 2, well, you do 8 divided by 2 is 4, that's 1. 4 divided by 2 is 2, that's 2. And 2 divided by 2 is 1, that's 3. So the answer for that logarithm would be 3 in that case. Obviously, for some constant b is greater than 1, but in computer science terms, we usually do a b is equal to 2. We learned about the linear function, which is where it is the function is dependent and equal to the data. So if we provide a data input of 150, we will get out a value of 150. So it is one-to-one with the data provided. We have an n log n function, which is similar. It takes in similar aspects of the logarithm function, but applies a scaling factor proportional to the linear function. So it has a curve of a logarithm, but also applies some linear aspect up to that, and has a faster growth rate than both the linear and the logarithm function, because you're getting this factor of n out front, multiplying each log, that log value. We have a quadratic function. These are often seen in nested for loops. When you iterate over your data set or your n once, that's linear, but then when you do it again, you are doing n times n, thus creating a quadratic function of n squared. So like an example, for I in range n and then for j in range n, like these are nested for loops iterating over the same sequence, thus creating a quadratic function of time complexity. And then obviously something similar is in cubic for looping over loops 3 times. And lastly, we have the exponential function, which is considered one of the slowest or least efficient, worst algorithm function we were shown in here. This one just basically, as we know the exponents, this raises your base value usually to the power of your data set. So for very large data sets, this creates an extremely large value provided and is extremely inefficient. So, but for smaller ones, it might be decent. So then we talked about asymptotic analysis, where we were introduced to big O notation. Now today was our first day learning big O, so I'm still learning these, but from my understanding is the big O notation describes the worst case scenario found or time complexity in the function, or describes the upper bound of the function. So as a whole, so it's pretty much like the bottleneck, right? The big O, it will only run as fast as its least performing function in a sense. So in the case of these functions outlined here, if you had a function or a polynomial, which is just a collection of kind of functions together with a constant and with an n, the constant function would be faster than the logarithm function or more efficient. But if these two are combined, your bottleneck is the logarithm function. So that one has the time complexity. If you have all 3 of these functions together, in one polynomial, well, your big O notation would be the linear function, because it is your bottleneck in that case, and would be the upper bound or as fast as or I'm not sure if that's the case exactly, because it says it's the worst case scenario. So in my ideas, the worst case scenario would be the slowest run, which would happen from the slowest function. Yeah. Then we have big omega notation, which describes the lower bound, which would also kind of refer to the function with the um, minimum or minimum growth rate of the function as a whole. So in order to determine this, you would kind of isolate the function within the polynomial, or that would have the fastest growth rate individually, thus creating a slow minimum growth rate for the function as a whole. And then we learned about big theta notation, which I'm still trying to understand fully. I think I'm gonna watch a few videos on big O, big omega, and big theta notation tonight. Just some very put it in simple terms videos to help solidify these concepts. Because big theta, I'm still a little bit um, I don't fully understand big theta that much. I understand that it's, yeah, I need to look further into these, but that's going to be it today. Let's get caught up on the chat here. Um, Jesus Zavaleta, thanks so much for joining. I appreciate you coming in and leaving a comment. I look forward to seeing you in the next stream. I know I'm about to wrap things up, so please come back tomorrow. I'll be here tomorrow. We can interact. JG says, I'm just starting a coding journey, but plan to learn Python later. That's awesome. What are you learning right now? Thank you for the follow, Joseph. I appreciate you on GitHub. All right, you guys, I'm going to go ahead and call it for today. Thanks so much for stopping in and checking in for today. Today was a long one. We streamed for 2 hours and 56 minutes, almost 3 hours. A lot of stuff introduced. We are almost done with chapter 3. We have a little bit less than 10 pages, and then we are good to move on and continue on. But I think we might really it might take us a while, honestly, to get through those chapter 3 problems. There's quite a few, probably 20 problems, and this is a lot of new material, so it might be a little bit difficult. But it's going to be just more practice, so we shouldn't be scared of anything. It'll be fun and all. We're solving problems, learning. It's all a part of the process. So thanks so much for joining me today, you guys. I'll be back tomorrow around the same time, so follow along, and I'll see you guys then. Peace out.